somewhere beyond the constellations we have named, beyond the light our instruments can gather, an invisible force draws hundreds of millions of galaxies toward a single region of space, a gravitational whisper so vast that even our own Milky Way drifts slowly, silently in its direction. This is the Great Attractor, a mass so immense it shapes the architecture of the cosmos itself, hidden from direct view behind the dense star fields of our own galaxy, known only by the gentle tug it exerts on everything within 500 million light-years. If these quiet journeys through the universe bring a measure of stillness to your evenings, a subscription ensures more will find their way to you. The breath can settle now, the shoulders soften, and the story of this unseen colossus unfolds from here. For thousands upon thousands of years, the night sky offered humanity a vision of perfect stillness. The ancient shepherds who watched their flocks beneath the stars of Mesopotamia, the sailors who navigated by the fixed patterns above the Mediterranean, the philosophers who gazed upward from the hills of Athens, all of them looked upon a cosmos that appeared eternal and unchanging. The stars held their positions night after night, year after year, generation after generation. Constellations that a grandmother pointed out to a child would remain in precisely the same arrangement when that child had become a grandparent themselves. This apparent permanence was so absolute, so reassuring in its constancy, that it seemed to speak of a universe designed for stability, a great celestial dome that had always existed and would continue to exist forever, its luminous points embedded like jewels in some vast and timeless architecture. The ancient Greeks imagined these stars fixed to crystalline spheres that rotated with mathematical precision around the Earth. Medieval astronomers refined these models with elaborate systems of circles upon circles, epicycles that explained the wandering motions of the planets while preserving the fundamental stillness of the stellar background. Even as our understanding of the heavens grew more sophisticated, even as Copernicus placed the sun at the center and Kepler described the elliptical paths of planets, the distant stars themselves remained a backdrop of reassuring immobility. They were so far away, so impossibly remote, that any motion they might possess was utterly imperceptible across the span of a human lifetime, or even across the span of recorded history itself. This vision of cosmic permanence persisted well into the 20th century. When astronomers spoke of the universe, they spoke of something static and eternal, a collection of stars that had always existed in more or less their present configuration. The very idea that the universe might have a history, that it might change and evolve on the grandest scales, seemed almost philosophically troubling. Even Albert Einstein, when he formulated his general theory of relativity in 1915, found that his equations suggested a universe that should either expand or contract. This implication disturbed him so deeply that he introduced an additional term, the cosmological constant, specifically to hold the cosmos in a state of perfect equilibrium. The notion of a static universe was not merely a scientific assumption. It was a kind of metaphysical comfort, a reflection of humanity's deep desire for permanence and stability in the face of earthly change. And then, in 1929, an astronomer named Edwin Hubble made an observation that would quietly transform everything we thought we knew about the nature of existence itself. Hubble worked at the Mount Wilson Observatory, perched in the mountains above Los Angeles, California, where a great reflecting telescope with a mirror 100 inches in diameter gathered the faint light of distant celestial objects. Night after night, Hubble trained this instrument on the spiral nebulae, those fuzzy patches of light that astronomers had long debated. Some believed these nebulae were merely clouds of gas within our own Milky Way galaxy. Others suspected they might be separate galaxies in their own right. Island universes scattered across an immensity of space far greater than anyone had previously imagined. Through careful observation and painstaking measurement, Hubble had already settled this question a few years earlier by identifying individual stars within the Andromeda Nebula and determining its distance. It lay far beyond the boundaries of our own galaxy, a separate collection of hundreds of billions of stars. But it was his subsequent work, analyzing the light from many such galaxies, that would prove even more consequential. Hubble examined the spectra of these distant galaxies, the rainbow-like spreads of color produced when their light was passed through a prism. He noticed that the spectral lines, the characteristic fingerprints left by various chemical elements, were shifted toward the red end of the spectrum. This phenomenon, known as redshift, indicated that the light waves had been stretched as they traveled through space. And stretched light waves meant that the objects emitting that light were moving away from us. The faster an object recedes, the greater its redshift, and Hubble found that the more distant a galaxy was, the faster it appeared to be moving away. This relationship, now known as Hubble's law, was elegant in its simplicity. Galaxies twice as far away were receding twice as fast. Galaxies 3 times as far were receding 3 times as fast. The pattern held with remarkable consistency across the depths of space. And the implication was profound. If all the distant galaxies were moving away from us, and if the most distant were moving fastest, then the universe itself must be expanding. Space was not a fixed stage upon which cosmic events unfolded. Space itself was growing, stretching, carrying the galaxies along with it like raisins in a rising loaf of bread. The static universe, that comforting vision of eternal stability, dissolved in the light of Hubble's observations. In its place emerged a cosmos in motion, a universe with a history, a creation that had begun at some finite moment in the past and had been expanding ever since. Einstein, upon learning of Hubble's findings, reportedly called his cosmological constant the greatest blunder of his career. The equations had been right all along. The universe was not standing still. This discovery introduced a new quantity into the vocabulary of cosmology, a number that would come to be called the Hubble constant. This value describes the rate at which the universe is expanding, typically expressed as a velocity per unit distance. A galaxy located 1 megaparsec away, roughly 3.2 million light-years, appears to recede from us at a certain number of kilometers per second. Hubble's original estimate of this value was considerably larger than modern measurements, but the essential insight remained valid. The universe was expanding at a rate that could be measured, quantified, and used to calculate backwards in time to an initial moment of cosmic beginning. From this expansion emerged the theoretical framework that would come to be known as the Big Bang. If the universe was expanding now, then it must have been smaller in the past. Running the clock backwards, the galaxies that are presently rushing apart must once have been closer together. Continuing this regression further and further into the past leads to a state of unimaginable density and temperature, a primordial condition from which all of space and time emerged. For decades, the Big Bang remained a theoretical construct, compelling but unconfirmed by direct observation. And then, in 1965, 2 radio astronomers working at Bell Telephone Laboratories in Holmdel, New Jersey, made an accidental discovery that would provide the most powerful evidence yet for this cosmological narrative. Arno Penzias and Robert Wilson were calibrating a large horn-shaped antenna originally built for satellite communication experiments. They were troubled by a persistent hiss, a faint but stubborn noise that seemed to come from every direction in the sky. They checked their equipment meticulously. They even removed a nest of pigeons that had taken up residence in the antenna and cleaned away the droppings, suspecting these might be the source of the interference. But the noise remained, constant and uniform, unchanging whether they pointed the antenna toward the galactic center or away from it, toward the sun or into the darkest patches of space. What Penzias and Wilson had detected, without initially realizing it, was the cosmic microwave background, the faint afterglow of the Big Bang itself. This radiation was the cooled remnant of the intense heat that had filled the early universe, light that had been traveling through space for billions of years, stretched by the expansion of the cosmos from its original high-energy state into the microwave portion of the electromagnetic spectrum. It arrived at Earth from every direction because it originated everywhere, at every point in the observable universe, at that ancient moment when the cosmos first became transparent to light. The uniformity of this radiation was striking. No matter where astronomers pointed their instruments, the cosmic microwave background appeared almost exactly the same intensity, the same temperature of approximately 2.7 degrees above absolute zero. This uniformity seemed to confirm a central assumption of modern cosmology, the cosmological principle, which holds that the universe, on the largest scales, is homogeneous and isotropic. Homogeneity means that matter and energy are distributed evenly throughout space. Isotropy means that the universe looks the same in every direction. There is no center, no edge, no preferred location or orientation. Every observer, anywhere in the cosmos, should see essentially the same large-scale structure. This principle was not merely a philosophical preference. It was a practical necessity for the mathematics of cosmology. If the universe were radically different in different directions, if matter were concentrated in some regions and absent from others in ways that varied from place to place, then the equations describing cosmic evolution would become impossibly complex. The cosmological principle allowed physicists to treat the universe as a smoothly expanding fluid, its behavior governed by elegant and tractable equations. By the 1970s, a satisfying picture of the cosmos had emerged from these discoveries and theoretical developments. The universe had begun in a hot, dense state approximately 10 to 20 billion years ago. The estimates varied, and had been expanding ever since. This expansion was uniform and isotropic, carrying all the galaxies away from one another like dots on the surface of an inflating balloon. The rate of this expansion was described by the Hubble constant, and the afterglow of the initial fireball could still be detected as the cosmic microwave background. Everything flowed outward from that primordial moment, like ripples spreading across the surface of a perfectly still pond. There was a peaceful beauty to this picture, a mathematical elegance that appealed to the scientific mind. The equations of general relativity, combined with the cosmological principle and the observed expansion rate, allowed cosmologists to model the entire history of the universe with remarkable precision. They could calculate the temperature of the cosmos at various epochs, predict the abundances of light elements forged in the first few minutes after the Big Bang, and trace the formation of galaxies and clusters of galaxies as gravity pulled matter together across billions of years. The motion of the cosmos seemed, in those years, to be fundamentally understood. Galaxies participated in the general expansion. their recession velocities determined by their distances according to Hubble's law. Local motions existed, of course. Neighboring galaxies tugged on one another gravitationally, producing peculiar velocities that superimposed themselves on the overall expansion. Our own Milky Way, for instance, was known to be approaching the Andromeda Galaxy, the two destined to merge billions of years hence. But these local motions were small perturbations on the grand cosmic flow, minor eddies in the universal outward current. Astronomers of that era might be forgiven for feeling that they had, at last, grasped the essential dynamics of the universe. The centuries of gazing at a seemingly static sky had given way to a dynamic but comprehensible cosmos, one whose past, present, and future could be read in the mathematics of expansion. The universe was large and old and expanding, but it was also, in a sense, orderly and predictable. The cosmological principle guaranteed that no great surprises awaited in any particular direction. Every patch of sky, every region of space, should behave like every other. And yet, as so often happens in the history of science, this confidence would prove premature. Beneath the elegant surface of the expanding universe, beneath the uniform glow of the cosmic microwave background and the steady march of Hubble's law, something was stirring. Something vast and unseen was exerting an influence that had not yet been detected, a gravitational pull so immense that it was affecting the motions of galaxies across hundreds of millions of light-years. The instruments of the 1970s were not quite sensitive enough to reveal this anomaly, and the theoretical framework of the time had not anticipated it. But it was there, patient and hidden, waiting to disturb the peaceful mathematics of cosmic expansion with its presence. In the years to come, astronomers would begin to notice that the universe was not flowing outward quite as smoothly as they had believed, and they would trace this disturbance to something they could not see, something they would eventually call the Great Attractor. In the vastness of space, there is a kind of motion that we have come to expect, a gentle drifting apart that belongs to the very fabric of the universe itself. This is the expansion we spoke of earlier, the Hubble flow, that patient recession of galaxies from one another as the cosmos slowly, steadily stretches in all directions. It is a motion without a center, without a destination, simply the quiet breathing of space-time itself as it carries everything within it along for the ride. And for many years, astronomers believed that this was the only large-scale motion that mattered, that once you accounted for the expansion of the universe, galaxies would appear more or less stationary relative to one another, each one sitting peacefully in its own little pocket of the cosmic web. But the universe, as it so often does, had something more subtle in store. There exists another kind of motion, one that sits on top of the Hubble flow like a secondary current running through an already flowing river. Astronomers call this peculiar velocity, and the name is rather fitting, because it refers to motion that is, in a sense, peculiar to each galaxy, motion that cannot be explained by the expansion of the universe alone. If a galaxy is moving through space faster or slower than the Hubble flow would predict, if it seems to be drifting in some particular direction beyond what the stretching of spacetime would account for, then that extra motion is its peculiar velocity. It is the fingerprint of gravitational influence, the signature of mass somewhere in the cosmos reaching out across the void and gently tugging on everything nearby. For a long time, these peculiar velocities were difficult to measure with any precision. The Hubble flow itself produces such enormous recession speeds at great distances that any additional motion seemed like a small perturbation, a minor wobble in the grand cosmic drift. But as telescopes grew more sensitive and measurement techniques grew more refined, astronomers began to notice that these peculiar velocities were not random at all. They were not scattered in every direction like leaves blown by a capricious wind. Instead, they seemed to follow a pattern, a coherent flow, as though vast regions of the universe were being drawn together toward some common destination. The story of how we came to understand this begins, as so many stories in astronomy do, with careful observation and a willingness to follow the evidence wherever it might lead. In 1976, the American astronomer Vera Rubin, working alongside her colleague Kent Ford, was engaged in a meticulous study of spiral galaxies. They were measuring the rotation curves of these galaxies, which is to say, they were observing how fast the stars and gas at different distances from the galactic center were orbiting around it. According to the physics that we understand from our own solar system, objects farther from the center of a gravitating mass should move more slowly, just as Neptune orbits the Sun more slowly than Mercury does. But Rubin and Ford found something unexpected. The stars at the outer edges of spiral galaxies were moving just as fast as those closer to the center, sometimes even faster, and this suggested that there was far more mass in these galaxies than the visible stars and gas could account for. Something unseen was providing additional gravitational pull, something that did not emit light or radio waves or any other form of radiation that our instruments could detect. This was one of the early and most compelling pieces of evidence for what we now call dark matter, and while Rubin's work was focused on the internal dynamics of individual galaxies, it hinted at a deeper truth about the cosmos. The universe contained far more mass than met the eye, and this hidden mass was shaping the motion of everything within it. If dark matter was influencing the rotation of stars within galaxies, it stood to reason that it might also be influencing the motion of galaxies themselves, drawing them together into clusters and superclusters, perhaps even pulling them in directions that had nothing to do with the simple expansion of space. Around the same time, in 1977, another piece of the puzzle fell into place. Researchers including Richard Henry and his colleagues were studying the cosmic microwave background radiation, that faint afterglow of the Big Bang that fills the entire sky with a nearly uniform warmth. This radiation is extraordinarily smooth, almost the same temperature in every direction you look, a testament to the remarkable homogeneity of the early universe. But when these astronomers looked very carefully, with instruments sensitive enough to detect tiny variations in temperature, they found something curious. The cosmic microwave background was not quite the same in all directions. There was a very slight asymmetry, a pattern called a dipole anisotropy, where the radiation appeared ever so slightly warmer in one direction of the sky and ever so slightly cooler in the opposite direction. This dipole pattern was not a relic of the early universe itself. It was not a feature imprinted on the cosmic microwave background at the moment of its creation. Instead, it was a consequence of our own motion through space. When you move toward a source of light, the light appears slightly blue-shifted, its wavelength compressed, its energy increased. When you move away from a source of light, the opposite occurs: a redshift, a stretching of wavelength, a cooling of color. The dipole anisotropy in the cosmic microwave background was telling us that the Earth, the Sun, the entire Milky Way galaxy, was moving through the universe at a considerable speed, racing toward one part of the sky and away from another. The confirmation of this motion came later that same year, from a team of astronomers working at the Lawrence Berkeley National Laboratory in California. Among them were George Smoot, who would later win the Nobel Prize in Physics for his work on the cosmic microwave background, and Mark Davis, a cosmologist with a deep interest in the large-scale structure of the universe. Using balloon-borne instruments and ground-based observations, they refined the measurement of the dipole anisotropy and calculated the speed at which our local group of galaxies, that gravitationally bound collection that includes the Milky Way, Andromeda, and several dozen smaller galaxies, was moving relative to the cosmic microwave background. The number they arrived at was striking. Our local group is traveling at approximately 600 kilometers per second, which is to say, 600,000 meters every single second, a velocity that seems almost incomprehensible from our earthbound perspective. To put this in some context, the fastest spacecraft humanity has ever launched travels at a small fraction of this speed. And yet here we are, our entire galactic neighborhood, hurtling through the cosmos at a pace that defies easy imagination. And the direction of this motion was equally significant. The local group is moving toward a region of the sky that lies in the direction of the constellations Centaurus and Hydra, a patch of the southern celestial hemisphere that, at the time, did not seem to contain anything particularly unusual. There were galaxies there, certainly, clusters of galaxies, the usual fare of the cosmic landscape, but nothing that immediately stood out as a gravitational anchor capable of pulling an entire neighborhood of galaxies along at such a prodigious speed. This was the puzzle that began to take shape in the minds of astronomers during those years. The motion was too fast, too coherent, too purposeful to be explained by random gravitational interactions between neighboring galaxies. It was not as though the Milky Way was simply orbiting Andromeda or being jostled by the gravitational influence of a few nearby clusters. The entire local group was moving together, and the direction of that motion pointed toward something distant, something massive, something that lay beyond the ordinary gravitational pull of our immediate surroundings. Imagine, if you will, a collection of leaves floating on the surface of a vast and tranquil sea. If the sea is perfectly still, the leaves will drift apart slowly as the water beneath them expands, carried along by gentle currents that have no particular direction. But now imagine that somewhere beneath the surface, far from view, there is a subtle flow, a current that draws the water in one direction, pulling the leaves along with it even as the sea continues to stretch. The leaves would still drift apart, obeying the general expansion of the water, but they would also move together in one direction, caught in an invisible river that ran beneath the surface of the sea. This is something like what astronomers were beginning to suspect about our corner of the universe. The Milky Way, Andromeda, the Magellanic Clouds, and all the other galaxies of the local group were being carried along by a flow that existed on top of the Hubble expansion, a peculiar velocity that pointed toward Centaurus and Hydra, toward something hidden in that direction of the sky. The universe was not just expanding. Something was pulling. But what could possibly exert such an influence? What manner of mass could reach across millions of light-years and gently but persistently tug on our entire galactic neighborhood, drawing us toward it at 600 kilometers per second? The visible galaxies in that direction, impressive as they were, did not seem sufficient to account for such a strong gravitational pull. There had to be more, something beyond what the telescopes could see, something that lay hidden behind the glare of the Milky Way or perhaps in a region of space that was difficult to observe for some other reason. This was the beginning of a long and patient investigation, one that would span decades and involve some of the most dedicated astronomers of their generation. The motion was real. The measurements were sound. but the cause remained elusive. And so the search began, a quiet and methodical effort to map the distribution of matter in that part of the sky, to measure the velocities of galaxies near and far, and to piece together the gravitational landscape that was shaping the flow of our cosmic neighborhood. In the chapters that follow, we will trace this search step by step, following the astronomers as they peered through the dust of the Milky Way, catalogued thousands of galaxies, and gradually assembled a picture of the enormous mass concentration that lay in the direction of our motion. For now, it is enough to rest with this image, this sense of gentle but persistent movement, this knowledge that we are not stationary in the cosmos but are instead being carried along by forces that reach across the vastness of space. The stars above us seem fixed in their places, the constellations unchanging from night to night, but in truth we are all in motion, our galaxy and its companions drifting together toward a destination that we are only beginning to understand. It is a slow journey, one that will take hundreds of millions of years to unfold, and yet it is happening right now, in this very moment, as you rest beneath the quiet sky. In the mid-1980s, a group of 7 astronomers came together across 3 continents to undertake what would become one of the most ambitious surveys of galactic motion ever attempted, and their collaboration would ultimately reveal a cosmic mystery so profound that it continues to shape our understanding of the universe to this day. These 7 researchers, working from observatories scattered across the Earth, would earn themselves a rather cinematic nickname, one borrowed from the celebrated 1954 film by Akira Kurosawa, and they would come to be known, with a certain affectionate admiration from their peers, as the 7 Samurai. The name suited them rather well, for like the warriors of that film, they had each brought distinct skills to a common cause, and together they would uncover something that none of them could have found alone. The members of this collaboration were Alan Dressler of the Carnegie Observatories in Pasadena, Sandra Faber from the University of California at Santa Cruz, David Burstein then at Arizona State University, Roger Davies who was working at the Kitt Peak National Observatory, Donald Lyndon Bell from the Institute of Astronomy in Cambridge, Roberto Turlevich also from Cambridge, and Gary Wegner of Dartmouth College. Each of these astronomers had spent years studying the properties and behaviors of galaxies, and each brought a particular expertise to the collective effort, whether in observational techniques, theoretical frameworks, or the careful statistical analysis that would be required to make sense of the vast quantities of data they intended to gather. Their collaboration began in earnest around 1986, though the relationships and preliminary discussions that made it possible had been forming for some years before that, as tends to happen in scientific endeavors of this scale and complexity. The fundamental question that drew them together was one that had been troubling astronomers for some time, and it concerned the peculiar motions of galaxies, those movements that could not be explained simply by the general expansion of the universe. When we observe distant galaxies, we see them receding from us, moving away as the fabric of space itself stretches and grows. And this universal expansion was first documented by Edwin Hubble in the 1920s. However, layered atop this cosmic expansion are additional motions, smaller perturbations caused by the gravitational influence of matter distributed unevenly throughout space, and these peculiar velocities, as they are called, can tell us a great deal about the distribution of mass in the universe, including mass that we cannot see directly. The 7 Samurai set out to map these peculiar velocities with unprecedented precision and scope, hoping to understand what gravitational forces might be tugging at our corner of the cosmos. To accomplish this ambitious goal, They employed a technique known as the dn-sigma relation, which provides a way to estimate the intrinsic luminosity of elliptical galaxies, and thus to calculate their true distances from Earth. Elliptical galaxies, those great spheroidal collections of ancient stars that lack the spiral arms and dust lanes of galaxies like our own Milky Way, have a useful property that makes them particularly suited to this kind of distance measurement. The stars within an elliptical galaxy orbit in many different directions, creating a range of velocities that can be measured by examining how the light from the galaxy is spread out across different wavelengths, a quantity called velocity dispersion and denoted by the Greek letter sigma. Larger and more luminous elliptical galaxies tend to have greater velocity dispersions, because their stronger gravitational fields require stars to move faster to maintain their orbits, and this relationship between a galaxy's apparent size, its velocity dispersion, and its intrinsic brightness allows astronomers to estimate how far away it truly lies. The dn-sigma relation, refined and calibrated through years of careful observation, gave the Seven Samurai a cosmic yardstick of remarkable precision, and over the course of their survey they used it to measure distances to more than 400 elliptical galaxies scattered across the sky. These galaxies lay within roughly 200 million light-years of Earth, which may sound like an incomprehensibly vast distance, and indeed it is. But in the context of the observable universe it represents a relatively local volume, a neighborhood of sorts within which the effects of nearby gravitational structures should be most clearly visible. By measuring both the distances to these galaxies and their velocities relative to us, the team could separate out the component of motion due to the universal expansion from the peculiar velocities caused by gravitational influences, and in doing so they began to construct a three-dimensional map of the cosmic flows in our region of space. What they found was unexpected and rather remarkable, though we shall describe it in measured terms as befits a discovery that took years of painstaking work to verify and understand. The peculiar velocities of the galaxies they surveyed were not random, not scattered in all directions as one might expect if they were responding to many small gravitational tugs from various nearby structures. Instead, there was a coherent pattern, a systematic flow of galaxies toward a particular region of space, and this flow extended far beyond our own local group of galaxies, beyond the Virgo cluster that dominates our immediate cosmic surroundings, beyond even the Great Hydra-Centaurus Supercluster that stretches across tens of millions of light-years. All of these structures, these vast collections of thousands upon thousands of galaxies, were moving together, streaming in the same general direction at velocities of several hundred kilometers per second, as though drawn by some enormous unseen mass lying beyond them. The team published their initial findings in 1987, in a paper that would reshape how astronomers thought about the large-scale structure of the universe, and it was in this publication that Donald Lyndon Bell proposed a name for the mysterious region toward which everything seemed to be flowing. He called it the Great Attractor, a term both descriptive and evocative, capturing the sense of an immense gravitational source exerting its influence across hundreds of millions of light-years of space. The name caught on immediately within the astronomical community and eventually with the broader public as well, for it had a certain poetry to it, a suggestion of cosmic majesty that spoke to the human imagination even as it described a purely physical phenomenon. Lyndon Bell, who had made many contributions to theoretical astrophysics over his long career, including important work on the dynamics of galaxies and the physics of black holes, had a gift for apt terminology, and the Great Attractor remains one of his most enduring linguistic contributions to the field. The mass required to produce such large-scale streaming motions was almost beyond comprehension, And the Seven Samurai calculated that the Great Attractor must contain the equivalent of tens of thousands of galaxies like our own Milky Way, all concentrated in a relatively compact region of space. Some estimates suggested a mass of around 10 to the 16th power solar masses, which is to say 10 million billion times the mass of our Sun, or roughly 10,000 times the mass of the Milky Way, including all its dark matter. Such an enormous concentration of matter would create a gravitational well of immense proportions, a basin in the fabric of space-time toward which everything in the surrounding regions would inevitably fall, slowly but persistently, over hundreds of millions and billions of years. The motions detected by the survey represented just a snapshot of this ongoing cosmic migration, a moment captured in the vast sweep of time during which galaxies drift ever so gradually toward their gravitational destiny. The location of this great mass, as determined by the direction of the galactic flows, lay approximately 150 to 250 million light-years from Earth, in the direction of the southern constellation Norma, which itself lies near the constellation Centaurus and Triangulum Australe. This region of the sky is particularly difficult to observe from Earth because it lies behind the dense plane of our own Milky Way galaxy, in what astronomers sometimes call the zone of avoidance. The stars, gas, and dust of our galaxy are concentrated in a band across the sky that corresponds to the galactic plane seen from within, and this material absorbs and scatters light from more distant objects, making it exceedingly difficult to see what lies beyond. It is rather like trying to peer through a thick fog bank to see the hills on the other side, except that this particular fog bank is made of billions of stars and vast clouds of obscuring dust, and it wraps around the entire sky in a great circle that we perceive as the Milky Way. This circumstance created a profound mystery, for here was evidence of an enormous mass, something with the gravitational pull of tens of thousands of galaxies, lying in a direction where we could not easily see what was there. The Great Attractor was inferred from its effects on the motion of surrounding matter, but the thing itself remained hidden, obscured by the very galaxy in which we reside. There was something almost poetic about this situation. The idea that one of the most massive structures in our cosmic neighborhood was rendered invisible to us by our own home galaxy, as though the universe were keeping a secret that we could only glimpse indirectly through the behavior of distant galaxies responding to forces we could measure but not see. The Seven Samurai were careful scientists, and they were well aware that extraordinary claims require extraordinary evidence, so they subjected their data to rigorous statistical analysis and invited scrutiny from their colleagues around the world. The existence of the large-scale flow toward the Great Attractor was controversial at first, as significant discoveries often are, and some astronomers questioned whether the effect might be an artifact of systematic errors in the distance measurements or biases in the sample of galaxies selected for study. These are the normal and healthy skepticisms of scientific practice, the mechanisms by which the community tests new ideas and separates genuine discoveries from measurement errors or wishful thinking. Over the following years, additional surveys by other teams would largely confirm the reality of the Great Attractor flow, though they would also reveal that the picture was more complex than initially supposed, with additional structures and flows contributing to the cosmic dance of galaxies in our corner of the universe. The discovery raised more questions than it answered, as the most important scientific discoveries often do. What exactly was the Great Attractor? What was the nature of the mass that could produce such enormous gravitational effects? And why was so much matter concentrated in that particular region of space rather than being more evenly distributed? These questions would occupy astronomers for decades to come, leading to new surveys, new observational techniques, and new theoretical frameworks for understanding the large-scale structure of the cosmos. The Seven Samurai had opened a door onto a mystery that extended far beyond their initial survey. A mystery that touched on fundamental questions about how the universe came to have the structure it does. How matter clumped together over billions of years to form the galaxies and clusters and superclusters that we observe today. And what forces and processes shaped this cosmic web of light and dark matter stretching across billions of light-years in every direction. For now, as we rest here in the gentle dark, we may simply appreciate the patient work of those 7 astronomers, who spent years gathering light from distant elliptical galaxies and measuring tiny shifts in spectral lines, all to trace the invisible currents of the cosmic ocean in which we float. Their collaboration exemplified the best aspects of scientific inquiry, the bringing together of diverse skills and perspectives, the careful collection and analysis of data, the willingness to follow the evidence wherever it led, and the intellectual courage to propose ideas that challenged existing assumptions about the universe. The Great Attractor, named in a paper now nearly 4 decades old, remains a subject of active research and ongoing discovery, its mysteries not yet fully resolved, its nature still being explored by new generations of astronomers with instruments that the 7 Samurai could scarcely have imagined when they began their work in the 1980s. When we gaze upward on a clear night, far from the lights of towns and cities, we see the Milky Way stretching across the heavens like a river of soft light. And this band of gentle luminescence has inspired wonder in every culture throughout human history, from the ancient Greeks who imagined it as spilled milk from the goddess Hera, to the Aboriginal Australians who saw in its dark lanes the shape of an emu running across the sky. Yet this same beautiful feature of our night sky, this glowing band that makes summer evenings feel magical and winter nights feel vast, presents one of the great frustrations of modern astronomy, because it blocks our view of a significant portion of the universe beyond, hiding galaxies and clusters and perhaps the very things we most need to see to understand why our corner of the cosmos moves as it does. This obscured region has come to be known as the zone of avoidance, a name that reflects not any physical property of space itself, but rather the practical reality that astronomers have long avoided this part of the sky when conducting surveys of distant galaxies, because the effort required to see through it seemed hardly worth the trouble when so much of the rest of the sky lay open and clear. The zone of avoidance encompasses roughly 20% of the celestial sphere, a substantial fraction of the heavens rendered murky and indistinct by the accumulated matter of our own galaxy lying between us and whatever wonders exist beyond. This matter takes several forms, each contributing in its own way to the veil that hangs before our eyes, and understanding these obstructions helps us appreciate both the difficulty of the problem and the ingenuity of the solutions that astronomers would eventually devise. The dust of the Milky Way consists of tiny grains, some no larger than a few molecules across, others perhaps a micrometer in diameter, and these particles are composed of silicates and carbon compounds and ices, the same sorts of materials we find in comets and asteroids but ground down to impossibly fine powder over billions of years of cosmic weathering. This dust does not so much block light as scatter it and absorb it preferentially, allowing longer wavelengths of red and infrared to pass through more easily while shorter wavelengths of blue and violet are scattered away, which is why distant stars seen through dusty regions often appear reddened, their light having been filtered through nature's own tinted glass. In the densest regions of the galactic plane, this dust can reduce the light from background objects by factors of tens or even hundreds, dimming galaxies that might otherwise be visible to the point where they become entirely undetectable by ordinary means. Beyond the dust lies the gas of the interstellar medium, primarily hydrogen in its various forms, along with helium and traces of heavier elements. And while this gas is far more transparent than the dust, it nonetheless contributes to the general obscuration by absorbing light at specific wavelengths and by adding to the general confusion of signals that astronomers must sort through when searching for faint and distant objects. Then there are the stars themselves. Millions upon millions of them crowded together along the galactic plane, creating a dense field of foreground objects that makes it exceedingly difficult to identify the more distant galaxies that lie beyond, like trying to spot a firefly in a distant meadow while standing before a wall of candles. Each of these factors combines with the others to create the zone of avoidance, a region where our otherwise excellent view of the cosmos becomes frustratingly opaque. It was into this zone of avoidance that the Great Attractor appeared to lie, positioned at galactic coordinates of approximately 320 degrees longitude and essentially 0 degrees latitude, which placed it almost precisely in the thickest part of the galactic plane, hidden behind the densest concentrations of dust and stars that our galaxy has to offer. The galactic coordinate system, it should be mentioned, is simply a way of describing positions in the sky using the plane of the Milky Way as a reference, with longitude measured around the galactic equator and latitude measured above or below it. So a latitude of 0 degrees indicates something lying directly in the plane itself, the worst possible location for observation through our galaxy's obscuring material. Throughout the late 1980s and into the early 1990s, this unfortunate cosmic geometry created genuine frustration among astronomers who had identified the peculiar velocities and calculated the approximate location of whatever mass concentration was responsible, only to find that nature had placed this object precisely where they could not observe it directly. Imagine, if you will, becoming aware through indirect evidence that something remarkable lies just beyond a frosted window, knowing approximately where it must be and approximately how massive it must be, yet being unable to simply wipe the glass clean and have a proper look. This was the situation facing cosmologists of that era, who possessed mathematical evidence of the Great Attractor's existence and influence but could offer no photographs, no spectra, no direct observations of any kind to satisfy the natural human desire to see what one is studying. This frustration motivated several astronomers to attempt what had previously seemed impractical, namely careful and painstaking surveys of precisely those regions that observers had long avoided, using techniques and patience that might reveal at least some of what lay hidden behind the galactic veil. Among the pioneers of this effort was René Kron-Korteweg, a Dutch astronomer working from the South African Astronomical Observatory, who undertook systematic optical surveys of the zone of avoidance beginning in the late 1980s and continuing through the 1990s. Her approach involved careful examination of photographic plates taken in regions that other astronomers had dismissed as too obscured to be useful, searching for the faint and reddened images of galaxies that might just barely peek through the thinner patches of galactic dust. This work required extraordinary patience and attention to detail, as the galaxies Kron-Korteweg sought were not obvious objects that would leap out from the images, but rather faint smudges that could easily be mistaken for artifacts or imperfections in the photographic emulsion, distinguished from stars only by their slightly fuzzy appearance and their failure to show the sharp diffraction spikes that bright stars produce. She and her colleagues developed techniques for identifying these obscured galaxies, learning to recognize the subtle signatures that distinguished a distant galaxy seen through dust from the many other features that could appear on deep photographic plates. And gradually their catalogues grew to include thousands of previously unknown objects lurking in the zone of avoidance. The southern hemisphere location of this work was essential, as the Great Attractor lies in the southern sky. in the direction of the constellations Centaurus and Norma, regions that never rise above the horizon for observers in the Northern Hemisphere. The South African Observatory, situated at Sutherland in the Karoo semi-desert, provided dark skies and good seeing conditions, and its position at latitude 32 degrees south allowed access to the crucial regions of sky where the Great Attractor was thought to reside. Kronkortueg's optical surveys revealed that the zone of avoidance was not entirely opaque, that patches of lower extinction existed where the dust was thinner and more distant galaxies could be glimpsed, and her work began to sketch in the rough outlines of the structures that lay hidden behind our galaxy's obscuring band. Yet optical surveys, even the most careful and thorough ones, could only accomplish so much, as the fundamental problem remained that visible light is absorbed and scattered by interstellar dust, and in the densest regions of the zone of avoidance, no amount of patience or technique could reveal what lay beyond. What was needed were observations at wavelengths that could pass through the dust more easily, that could penetrate where visible light could not. And fortunately, the physics of electromagnetic radiation provided several such windows through which astronomers could peer. Radio waves, with their much longer wavelengths measured in centimeters rather than the tiny fractions of a micrometer that characterize visible light, pass through interstellar dust almost entirely unimpeded, and this property made radio telescopes natural tools for exploring the zone of avoidance. Of particular usefulness is the emission from neutral hydrogen atoms at a wavelength of 21 centimeters, which arises when the single electron in a hydrogen atom flips its spin relative to the proton in the nucleus, a transition that releases a tiny amount of energy in the form of a radio photon. This 21-centimeter emission serves as an excellent tracer of galaxies because galaxies contain enormous quantities of neutral hydrogen gas, and by detecting this emission astronomers can locate and study galaxies that are completely invisible at optical wavelengths. In 1995, the Parkes Radio Telescope in New South Wales, Australia, began a systematic survey of neutral hydrogen emission in the zone of avoidance, using the 21-centimeter line to search for galaxies hidden behind our own. The Parkes telescope, a 64-meter dish that had been operating since 1961 and had previously achieved fame for receiving television signals from the Apollo 11 moon landing, was ideally suited for this work, possessing both the sensitivity to detect faint signals and the geographic location to observe the southern sky where the Great Attractor lay hidden. The survey, which became known as the H.I. Parkes All-Sky Survey or HIPAS, eventually covered the entire southern sky visible from Australia, but its most revelatory work came in the zone of avoidance itself, where it detected hundreds of galaxies that no optical telescope could possibly have seen. The radio observations revealed that the zone of avoidance was densely populated with galaxies, not empty as it appeared to optical eyes but rather teeming with objects that the dust had hidden from view. These detections came as velocity measurements as well, because the 21-centimeter emission line shifts in frequency depending on whether the emitting galaxy is moving toward or away from us, providing not just positions on the sky but also information about how fast each galaxy is receding and therefore approximately how far away it lies. The Parkes survey thus added both spatial and kinematic information about the hidden structures in the zone of avoidance, helping astronomers to understand not just where galaxies lay but how they moved and therefore how mass was distributed in this previously obscure region of the universe. Around the same time that the Parkes radio survey was underway, another observational window was being exploited with remarkable success, namely the near-infrared portion of the electromagnetic spectrum, where wavelengths are longer than visible light but shorter than radio waves, and where interstellar dust is much more transparent than at optical wavelengths. The 2-micron all-sky survey, known as 2MASS, began observations in 1997 using twin automated telescopes, one at Mount Hopkins in Arizona and the other at Cerro Tololo in Chile, chosen so that together they could observe the entire sky from both northern and southern hemispheres. These telescopes observed at wavelengths of approximately 1 to 2 micrometers, in the near-infrared bands designated J, H, and K, where the extinction from interstellar dust is roughly 1/10 what it is at visible wavelengths. The 2MASS survey ultimately detected millions of galaxies across the entire sky, but its most dramatic revelations came once again in the zone of avoidance, where it unveiled thousands of galaxies that had been completely hidden from optical view. Infrared light, being less affected by dust, penetrated regions that visible light could not, and the resulting images showed a zone of avoidance that was not a void at all, but rather a richly populated region of the universe that happened to lie behind our galaxy's dusty plain. The 2MASS extended source catalog, which included all the galaxies detected by the survey, became an essential resource for understanding the large-scale structure of the nearby universe, revealing filaments and clusters and walls of galaxies that extended right through the zone of avoidance as though our galaxy's obscuring band were not there at all. Through these various efforts, using optical surveys where the dust was thinnest, radio observations that ignored the dust entirely, and infrared observations that penetrated it substantially, the zone of avoidance gradually yielded its secrets, and the structures within it began to emerge like shapes materializing through fog on a quiet morning. Where once there had been only hints and suspicions based on peculiar velocities and mathematical inference, now there were actual observations of actual galaxies, their positions and velocities measured and catalogued, their contributions to the gravitational landscape of the nearby universe gradually becoming clear. Among the most significant discoveries to emerge from this unveiling was the true nature of a cluster previously known as Abell 3627, which lies in the constellation Norma near the heart of the zone of avoidance, at a position remarkably close to where the Great Attractor was predicted to lie. Earlier observations had identified this cluster but had vastly underestimated its significance, because the optical surveys upon which the original Abell catalogue was based could only detect the cluster's brightest members through the thick foreground extinction. As the newer surveys penetrated the dust, astronomers realized that Abell 3627 was not a modest cluster of a few dozen galaxies, as it had appeared in optical images, but rather an enormous concentration of thousands of galaxies, one of the richest clusters in the nearby universe. This cluster came to be called the Norma cluster, named for the constellation in which it appears, and its properties were remarkable by any measure. The Norma cluster lies at a distance of approximately 200 million light-years from us, which places it in precisely the region where the Great Attractor was expected to reside based on the peculiar velocity observations. Its mass has been estimated at several times 10 to the 15th solar masses, making it one of the most massive concentrations of matter within several hundred million light-years of the Milky Way. The cluster contains numerous giant elliptical galaxies, the massive spheroidal systems that are typically found at the centers of large clusters, along with hundreds of smaller galaxies of various types, all bound together by their mutual gravitational attraction into a system spanning several million light-years across. The discovery of the Norma cluster's true richness marked a turning point in the search for the Great Attractor, providing at last a visible, tangible structure that could account for at least part of the gravitational attraction that had been inferred from peculiar velocity observations. Here was not a mysterious invisible force or some exotic form of matter, but rather a straightforward if enormous collection of galaxies, hidden from view only by the accident of cosmic geometry that placed it behind our galaxy's dusty plane. The frustration of the preceding years began to give way to the satisfaction of finally seeing what had been pulling us all along, though as further observations would reveal, the Norma cluster was itself only part of a much larger story. The techniques developed during this era of zone of avoidance exploration continue to be refined and applied today, with newer surveys at ever longer wavelengths and with ever greater sensitivity revealing additional details of the structures hidden behind our galaxy. The zone of avoidance remains a challenging region to study, but it is no longer the impenetrable barrier it once seemed, and the galaxies within it now take their place in our maps of the cosmic web alongside those in clearer parts of the sky. The gradual unveiling of this hidden 20% of the universe stands as a testament to the persistence of astronomers who refuse to accept that any region of the cosmos should remain forever beyond our knowledge, and who developed the tools and techniques necessary to see what had previously been unseeable. The Norma cluster sits quietly in the southern sky, occupying a region of space approximately 150 million light-years from our own Milky Way galaxy, and it is here, in this relatively nearby pocket of the cosmos, that astronomers first believed they had found the source of that mysterious gravitational tug we have come to call the Great Attractor. The cluster itself is a substantial gathering of matter, home to several thousand individual galaxies that orbit slowly around a common center of mass, each one contributing its own gravitational influence to the collective whole, and together they form one of the more massive structures in our local region of the universe. To observe the Norma cluster directly has always presented certain challenges, as we have discussed, owing to its unfortunate position behind the dense star fields and obscuring dust lanes of our own galaxy's central plane. But patient astronomers working across multiple decades have gradually assembled a portrait of this distant congregation, revealing it to be a place of considerable gravitational significance. At the heart of the Norma cluster resides a particularly imposing galaxy known by its catalogue designation ESO 137-006, and this massive elliptical system serves as a kind of gravitational anchor around which the other cluster members arrange themselves. Elliptical galaxies of this type represent some of the most massive individual structures in the universe, having grown large through countless mergers and acquisitions over billions of years, slowly absorbing smaller galaxies that wandered too close, incorporating their stars and gas and dark matter into an ever-growing whole. ESO 137-006 exemplifies this process of cosmic accumulation, sitting heavy and luminous at the cluster's center, its smooth elliptical shape betraying none of the spiral arms or distinct features we associate with younger, more dynamically active systems. The galaxy simply glows with the combined light of hundreds of billions of elderly stars, most of them past their prime, burning steadily through the long twilight of their stellar lives. During the 1990s, a space-based observatory known as ROSAT turned its sensitive instruments toward the Norma cluster, seeking to observe not the visible light of its constituent galaxies, but rather the X-ray emissions that would reveal the presence of extremely hot gas filling the spaces between them. ROSAT, which is short for Roentgen Satellite, a German-led mission with contributions from the United States and the United Kingdom, carried detectors specifically designed to capture these high-energy photons that our atmosphere would otherwise absorb before they could reach ground-based telescopes. What the observations revealed confirmed what astronomers had suspected but could not previously demonstrate with such clarity, namely that the Norma cluster contains vast quantities of superheated gas, material heated to temperatures of millions of degrees by the immense gravitational forces at work within the cluster's boundaries. This hot gas, sometimes called the intracluster medium, represents a significant fraction of the normal matter contained within any massive cluster of galaxies, and its temperature provides a direct measurement of the gravitational potential well in which it sits. The hotter the gas, the deeper the gravitational well must be to hold it in place, and the deeper the well, the more mass must be present to create it. Through this reasoning, the Rosat observations allowed astronomers to estimate the total mass of the Norma cluster with greater confidence than previous methods had permitted, and the numbers they derived were substantial indeed, suggesting a structure massive enough to exert significant gravitational influence on the galaxies surrounding it. The hot gas itself glows brightly in X-rays, creating a diffuse halo of emission that traces the cluster's overall shape and extent, providing a map of sorts that reveals how matter has distributed itself under gravity's patient guidance. Yet even as these observations confirmed the Norma cluster's impressive credentials, a troubling realization began to dawn on the researchers attempting to account for the Great Attractor phenomenon. When they tallied up all the mass they could detect within and around the Norma cluster, including the galaxies themselves, the hot intracluster gas, and the dark matter whose presence they could infer from gravitational effects, the total simply did not add up to what the observed peculiar velocities required. The Great Attractor, as measured by the streaming motions of thousands of galaxies in our cosmic neighborhood, seemed to demand a mass concentration even larger than what the Norma cluster could provide on its own. Something was missing from the accounting, some additional source of gravitational pull that had not yet been properly identified or appreciated, and this discrepancy sent astronomers searching deeper into space, looking beyond the Norma cluster for whatever else might be contributing to this cosmic tug-of-war. The answer, it would turn out, lay considerably farther away than anyone had initially supposed, in a direction that aligned suspiciously well with the Great Attractor's apparent location, but at a distance roughly 4 times greater. There, approximately 650 million light-years from Earth, sprawls an enormous concentration of matter known as the Shapley Supercluster, named in honor of the American astronomer Harlow Shapley, who first drew attention to this remarkable gathering of galaxies in 1930. Shapley himself was a pivotal figure in the history of astronomy, known primarily for his work in determining the size and structure of our own Milky Way galaxy, and for his role in the great debate with Heber Curtis over whether the spiral nebulae were island universes in their own right or merely components of our own stellar system. His identification of what would later bear his name came almost incidentally, as he noted an unusual concentration of galaxies in the southern constellation of Centaurus while conducting broader surveys of the sky. 4 decades following Shapley's initial observation, this distant concentration received relatively little attention from the astronomical community, overshadowed by more accessible targets and hampered by the same problems of galactic obscuration that plagued observations of the Norma cluster. The Shapley Supercluster lies in roughly the same direction as the zone of avoidance, requiring observers to peer through or around the same curtain of dust and stars that conceals the Great Attractor region, and this circumstance delayed a full appreciation of its significance. It was not until the late 1980s that researchers began to seriously consider the possibility that this distant structure might play a major role in the gravitational dynamics of our local universe, and when they did, the implications proved quite remarkable. In 1989, an astronomer named Somak Rekordahari published an analysis suggesting that the Shapley supercluster represented a far more significant concentration of mass than had been previously appreciated, and that its gravitational influence might extend far enough to affect the motions of galaxies in our own cosmic neighborhood. Recorder-Hurry's work drew on improved surveys of galaxy distributions and redshift measurements that allowed for more accurate distance estimates, painting a picture of a structure so massive that it could not be ignored in any serious attempt to understand large-scale cosmic flows. 2 years later, in 1991, Roberto Scaramella and colleagues published their own investigation, arriving at similar conclusions through somewhat different methods, and together these studies began to shift the conversation about the Great Attractor in a significant new direction. What Recorder-Hurry and Scaramella and their collaborators had found suggested that the gravitational landscape of our local universe was considerably more complex than the simple picture of a single attractor implied. Rather than one dominant mass concentration pulling everything toward itself, there appeared to be multiple structures at different distances, each contributing its own gravitational influence to the observed peculiar velocities of nearby galaxies. The Norma cluster remained significant, certainly, but it now seemed to occupy a kind of intermediate position in a larger gravitational hierarchy, itself being pulled toward the even more massive Shapley supercluster while simultaneously tugging on us and our neighboring galaxies. This arrangement suggested a cascading series of attractions, a gravitational relay race in which matter falls toward ever larger concentrations in a cosmic game of follow the leader. The Shapley supercluster itself is a genuinely enormous structure, spanning tens of millions of light-years and containing within its boundaries numerous individual galaxy clusters, each one a significant gravitational entity in its own right. Current estimates suggest that its total mass may approach something like 10,000 times the mass of our own Milky Way galaxy, a quantity so large that it beggars ordinary comprehension yet still represents only a tiny fraction of the observable universe as a whole. Within this sprawling complex, individual clusters orbit slowly around their common center of mass, their constituent galaxies moving within them like fish in separate but interconnected aquariums, and the whole assembly participates in the general expansion of the universe while simultaneously generating the gravitational wells that cause local deviations from that expansion. The emerging picture, as astronomers incorporated these new findings into their models, was one of nested structures and layered influences, a cosmic hierarchy in which the Great Attractor might represent not so much a final destination as a waypoint along a longer journey. Our own local group of galaxies falls toward the Virgo cluster, and the Virgo cluster falls toward the Great Attractor region and the Norma cluster contained within it, and the Norma cluster in turn falls toward the Shapley supercluster, and whether there exists some still larger structure beyond Shapley toward which everything continues to stream remains a question for future observations to resolve. This cascade of attractors, each one embedded within the gravitational embrace of the next, suggests that the universe's structure is rather like a series of increasingly large whirlpools, each one swirling around its own center while simultaneously being drawn into the circulation of a still larger vortex. The mystery of the Great Attractor, rather than being solved by these discoveries, deepened in a way that illuminated the true complexity of cosmic structure. What had seemed at first like a simple puzzle, identify the mass responsible for observed galaxy motions, had transformed into a window onto the hierarchical nature of the universe itself, revealing how matter organizes into ever larger associations under gravity's patient influence. The Norma cluster remained important, the hot gas revealed by Rosat observations confirming its substantial mass, but it could no longer claim sole responsibility for the peculiar velocities that had first drawn attention to this region of space. Behind it, 4 times farther away but proportionally more massive, the Shapley supercluster loomed as the deeper truth behind the Great Attractor phenomenon. Understanding this layered structure requires a certain comfort with the vast scales involved, both in space and in time. The light we observe from the Shapley Supercluster left those galaxies some 650 million years ago, departing when life on Earth had not yet ventured onto land, when the oceans teemed with strange Paleozoic creatures whose descendants would eventually give rise to everything we know as terrestrial biology. In the time it has taken that light to reach us, civilizations have risen and fallen without notice by the cosmos. Continents have drifted across the face of our planet, and the galaxies themselves have continued their slow migration toward destinations they will not reach for billions of years yet to come. The gravitational interactions we observe are equally patient, operating on timescales that make human history seem like the briefest flicker, and the structures they create persist for eons, evolving slowly under influences that we are only beginning to comprehend. In the year 2014, two astronomers published a paper in the journal Nature that would quietly reshape our understanding of where we live in the cosmos. Their names were R. Brent Tully, working at the Institute for Astronomy at the University of Hawaii, and Hélène Courtoise, working at the University of Lyon in France. These two researchers, along with their collaborators, had spent years gathering data on how galaxies move through space, and what they discovered was something rather beautiful, a way of mapping the universe not by where things are, but by where things are going, by the gentle and persistent pull of gravity that guides everything, including us, through the darkness between the stars. Brent Tully had been studying the large-scale structure of the universe for decades by this point, and he was particularly interested in the peculiar velocities of galaxies, which is to say, the component of their motion that cannot be explained simply by the expansion of the universe. Every galaxy is moving away from every other galaxy due to cosmic expansion, but on top of that general drift, each galaxy has its own individual motion, pulled this way or that by the gravitational influence of whatever mass happens to be nearby, or not so nearby, or quite far away indeed. These peculiar velocities are like currents in a vast ocean, and by mapping them carefully, one can begin to see the shape of the underlying gravitational landscape, the hills and valleys of mass that guide the flow of everything. Hélène Courtoise brought to this collaboration her expertise in observational techniques and her deep interest in cosmic cartography, the science of mapping the universe at its largest scales. Together, Tully and Courtoise assembled something called the Cosmic Flows 2 database, which contained the measured velocities of approximately 8,000 galaxies. 8,000 galaxies is a small number compared to the total population of galaxies in the observable universe, which runs into the hundreds of billions, but it was enough to begin sketching the broad outlines of the gravitational structures that shape our region of space, and that was precisely what they intended to do. The challenge with measuring galaxy velocities is that you cannot simply look at a galaxy and know how fast it is moving toward you or away from you in absolute terms. What you can measure is the redshift, the stretching of light that tells you a combination of two things at once: the recession velocity due to cosmic expansion and the peculiar velocity due to local gravitational influences. Separating these two components requires knowing the distance to each galaxy independently of its redshift, and measuring cosmic distances is famously difficult, involving careful observations of standard candles like Cepheid variable stars or Type Ia supernovae, or using relationships between a galaxy's properties that can serve as rough distance indicators. The Cosmic Flows 2 database represented an enormous effort to compile such distance measurements for thousands of galaxies, allowing the peculiar velocities to be extracted and mapped. Once you have a collection of peculiar velocities scattered across the sky, you need some mathematical technique to turn those scattered measurements into a smooth picture of the underlying gravitational field. The technique that Tully, Courtois, and their collaborators employed is called a Wiener filter, named after the mathematician Norbert Wiener, who developed it in the 1940s for applications in signal processing. The Wiener filter is a way of extracting the most likely true signal from noisy data, balancing what the data are telling you against what you expect on theoretical grounds. In the context of cosmic velocity flows, the Wiener filter takes the measured peculiar velocities and reconstructs the smoothest gravitational field that is consistent with both the observations and our understanding of how matter should be distributed in the universe according to the standard cosmological model. The result of applying this technique was a three-dimensional map of the gravitational basins of attraction in our region of the cosmos. A basin of attraction, in this context, is a region of space within which all the galaxies are flowing toward a common center, drawn by the combined gravitational pull of all the mass concentrated in that direction. It is much like a watershed on the surface of the Earth, where all the raindrops falling within a certain region will eventually flow into the same river and make their way to the same ocean. The boundaries between these basins are surfaces where the flow changes direction, where a galaxy on one side will drift toward one center while a galaxy on the other side will drift toward a different center entirely. What Tully and Courtois found, when they drew these boundaries on their map, was that our own galaxy, the Milky Way, along with all the familiar structures nearby, the local group, the Virgo cluster, the entire Virgo supercluster that had previously been considered our home supercluster, all of this was contained within a single enormous basin of attraction. This basin was far larger than anyone had previously appreciated, spanning approximately 500 million light-years across, and containing roughly 100,000 galaxies within its boundaries. They had discovered that our cosmic neighborhood was much larger than we had thought, and they needed a name for it. The name they chose was Laniakea, a Hawaiian word meaning immeasurable heaven. This name was suggested by Noire Napoleon, a Hawaiian language expert, and it seemed fitting for the Institute for Astronomy at the University of Hawaii to honor the indigenous language and culture of the islands where Brent Tully had done so much of his work. The word itself carries a sense of vastness and wonder, immeasurable heaven, and it describes well the sheer scale of what had been discovered. A structure so large that light takes 500 million years to cross it, containing more galaxies than any human could hope to count in a lifetime of counting. Within Laniakea, the galaxies are all falling toward a common gravitational center, and that center lies in the direction of the constellations Norma, Hydra, and Centaurus, precisely where the Great Attractor had been identified decades earlier. The Great Attractor, that mysterious concentration of mass hidden behind the plane of our own galaxy, sits near the gravitational heart of Laniakea. It is not necessarily the only source of attraction, for there are other concentrations of mass within this vast basin, including the Centaurus cluster and the Norma cluster and the various walls and filaments of galaxies that thread through this region. But the overall flow of galaxies within Laniakea is directed roughly toward this central region, including our own flow, our own gentle fall through the darkness. The Milky Way is moving toward the gravitational center of Laniakea at a velocity of approximately 600 kilometers per second. This is quite fast by everyday standards, faster than any vehicle humans have ever built, faster than the Earth moves around the Sun, faster than the Sun moves around the center of the Milky Way. And yet, at cosmic scales, it is a gentle drift, a slow migration that has been going on for billions of years and will continue for billions more. The distances involved are so vast that even at 600 kilometers per second, we would need tens of billions of years to reach the center of Laniakea, if we could reach it at all. But here is where the story takes a turn that is neither dramatic nor alarming, simply a quiet fact about the nature of our universe. We will never arrive at the gravitational center of Laniakea. The same dark energy that was discovered in 1998, the mysterious force that is causing the expansion of the universe to accelerate, will eventually overcome the gravitational attraction that is currently pulling us inward. As the universe continues to expand, and as that expansion accelerates, the distances between the large-scale structures will grow faster than gravity can overcome. The galaxies within Laniakea will continue to fall toward each other for now, but eventually the expansion will win, and the components of Laniakea will drift apart, each cluster and group of galaxies becoming isolated in an increasingly empty cosmos. This is not something that will happen soon, by any reasonable definition of soon. The current epoch is one in which gravity still dominates at the scales of galaxy clusters and superclusters, and Laniakea will remain a coherent structure for billions of years to come. But in the very long run, in the deep future of the universe, the concept of a supercluster will cease to have meaning, as dark energy stretches space faster than any gravitational basin can hold itself together. We are, in a sense, living in a privileged time, a time when the universe is structured and interconnected in ways that will not last forever. The boundaries of Laniakea, as mapped by Tully and Kurzweil, represent the surfaces where the gravitational flow changes direction. On one side of the boundary, galaxies are falling toward the center of Laniakea. On the other side, they are falling toward the centers of neighboring superclusters, structures with names like Perseus Pisces and Shapley and Coma, each one its own immense basin of attraction, each one containing its own hundreds of thousands of galaxies. The universe at this scale is a patchwork of such basins, each one defined not by its contents but by its flows, by the direction in which everything within it is moving. This way of thinking about cosmic structure was itself a contribution of the Tully-Kurzweil work. Previous definitions of superclusters had been based on the density of galaxies, on finding regions where galaxies are more concentrated than average and drawing boundaries around them. But the velocity-based definition is more physically meaningful, because it reflects the actual gravitational influence that is shaping the distribution of matter. A supercluster defined by density is just a description of where things happen to be at this moment. A supercluster defined by velocity flow is a description of where things are going, of the underlying gravitational architecture that will determine the future evolution of the cosmic web. There is something poetic in the realization that we now know our cosmic address with a precision that was unimaginable a century ago. We live on a small planet orbiting a medium-sized star in the outer regions of a spiral galaxy we call the Milky Way. The Milky Way is part of a small gathering of galaxies called the Local Group, which is falling toward the Virgo cluster, which is itself part of the larger Virgo supercluster. And all of this, the whole familiar neighborhood stretching out for tens of millions of light-years, is contained within the vastly larger structure called Laniakea, our home among the superclusters, our place in the immeasurable heaven. The Great Attractor, that enigmatic concentration of mass that first puzzled astronomers in the 1970s and 80s, is no longer quite so mysterious. It is simply the gravitational center, or near to the center, of the supercluster we call home. It is the place toward which we are falling, along with 100,000 other galaxies, each one drifting through the darkness in response to the gentle and invisible pull of gravity. We will never reach it, because the universe itself is expanding faster than we can fall, but that does not diminish the beauty of the journey, or the wonder of knowing, at last, where we are and where we are going. In the quiet darkness between the galaxies, where the light of stars fades to nearly nothing, the great structures of the cosmos maintain their patient vigil. The filaments and walls and clusters and superclusters, all of them shaped by gravity, all of them defined by the flow of matter through the void. Laniakea is our home within this architecture, a structure so large that the human mind can barely comprehend it, and yet somehow comprehensible nonetheless, thanks to the patient work of astronomers like Brent Tully and Helene Couttoise, who measured the velocities of thousands of galaxies and drew, at last, a map of where we live. And so we drift, gently and imperceptibly, toward the heart of Laniakea, pulled by the same force that holds us to the Earth and the Earth to the Sun and the Sun to the galaxy. Gravity, the weakest of the fundamental forces and yet the one that shapes the largest structures in existence, guides us through the cosmos in a motion so slow and so steady that it is indistinguishable from stillness. The universe is vast and quiet and very, very patient, and we are part of it, falling forever toward a center we will never reach, at home in the immeasurable heaven. Let us turn our attention now to something that cannot be seen, and yet accounts for most of what exists, a kind of matter that emits no light and reflects no light and absorbs no light, and yet without which the galaxies themselves would fly apart like dandelion seeds in a gentle wind, unable to hold themselves together, unable to cluster, unable to form the great cosmic structures that we have been describing in these quiet hours together. When astronomers first calculated the mass of the Great Attractor region, they encountered a problem that had become familiar to them over many decades of looking carefully at the universe, which is that the numbers did not add up in the way one might expect, not even close, not by a factor of 2 or 3 but by a factor of 5 or 6 or more, depending on how one performed the measurements and which techniques one employed. And this discrepancy pointed toward a truth that we are still working to understand, which is that the visible matter in the universe, all the stars and gas and dust and planets and moons and everything we can detect with our telescopes across all wavelengths of light, constitutes only a small fraction of what is actually there, perhaps 15 or 20% of all matter, with the rest being something we call dark matter. Not because it is necessarily dark in any sinister sense, but simply because it does not interact with light in any way that we can observe. The Great Attractor's gravitational influence is far too strong to be explained by the galaxies we can see in that direction, even accounting for all the hot gas between galaxies and all the dim dwarf galaxies that might escape casual notice. And so we are forced to conclude, as astronomers have been forced to conclude again and again when examining large cosmic structures, that most of the mass doing the pulling is invisible to us, present only through its gravitational effects, shaping the motions of galaxies and the paths of light itself while remaining forever hidden from direct view, like a hand moving beneath a silk cloth, visible only through the motion it creates in the fabric above. This idea of invisible matter has a history that stretches back nearly a century now, to a time when astronomers were first beginning to understand that galaxies were not merely individual islands scattered randomly through space but often gathered together in clusters, bound by gravity into communities of hundreds or thousands of members. And one of the first people to look carefully at such a cluster and ask serious questions about its mass was a Swiss astronomer named Fritz Zwicky, working at the California Institute of Technology, a man known for his brilliance and also for his difficult temperament and his willingness to propose ideas that others found strange or premature. In 1933, Zwicky turned his attention to the Coma Cluster, a rich gathering of galaxies located in the direction of the constellation Coma Berenices, about 300 million light-years from Earth, containing over 1,000 galaxies bound together in a roughly spherical arrangement several million light-years across. And he wanted to know how much mass the cluster contained, because understanding the mass would help explain how such structures formed and how they held together and what the universe might be like on the largest scales. Zwicky had two ways to estimate the mass, and this is where the problem emerged, because the two methods gave answers that disagreed dramatically, and rather than dismissing this disagreement as experimental error or measurement uncertainty, Zwicky took it seriously and followed the logic wherever it led, which was to a conclusion that would take decades for the astronomical community to fully accept. The first method was simply to count up all the galaxies in the cluster and estimate how much mass each one contained based on its brightness, since brighter galaxies generally contain more stars and therefore more mass, and this gave a certain number, a very large number to be sure, trillions upon trillions of solar masses, but a number that could be calculated and written down and compared to other estimates. The second method was more subtle and involved watching how the galaxies moved within the cluster, measuring their velocities through the Doppler shift of their light, and using these velocities to infer how much gravitational pull was needed to keep the cluster bound together. Because if the galaxies were moving too fast for the gravity present to hold them, they would fly apart and disperse into the surrounding void. And yet the Coma Cluster had clearly been there for billions of years, stable and coherent, its members orbiting around their common center of mass in a cosmic dance that showed no signs of dissolution. When Zwicky applied this second method, using what is called the virial theorem from classical mechanics, he found that the cluster required far more mass than the visible galaxies could account for, perhaps 400 times more in his original calculation, though later refinements would revise this to a still enormous factor of about 5 or 6. And this missing mass, this vast invisible component, he called Dunkel Materie, which is simply the German phrase for dark matter, a name that has stuck with us ever since, now appearing in thousands of scientific papers every year as astronomers around the world continue to search for clues about what this substance might actually be. Zwicky's contemporaries were not immediately convinced, and the dark matter hypothesis languished for several decades in a kind of scientific limbo, neither fully accepted nor entirely rejected, waiting for additional evidence that would eventually arrive through the patient work of other astronomers examining other systems, including the rotation curves of spiral galaxies measured by Vera Rubin and Kent Ford in the 1970s, which showed that stars in the outer regions of galaxies were orbiting far too quickly to be held by the gravity of visible matter alone. And this was the evidence that finally convinced most astronomers that dark matter was real, that Zwicky had been right all along, even if we still did not know, and still do not know, what dark matter actually is. Today we have a third method for detecting dark matter, one that Zwicky himself might have appreciated, and this method relies on the bending of light predicted by Einstein's general theory of relativity, which tells us that massive objects curve the fabric of space-time and that light traveling through this curved space-time will follow curved paths, so that a massive cluster of galaxies can act as a kind of cosmic lens, bending and focusing the light from more distant galaxies behind it, creating distorted arcs and multiple images and subtle stretching effects that can be measured with careful observation. The Hubble Space Telescope has been particularly valuable for this work, floating above the blurring effects of Earth's atmosphere and providing the sharp images needed to detect the tiny distortions caused by gravitational lensing. And astronomers have used these observations to map the distribution of mass in galaxy clusters, finding that the mass traces out a pattern quite different from the pattern of visible light, with the dark matter forming a vast extended halo around the luminous galaxies, like a cloud of invisible fog within which the visible matter is merely the densest condensation. In the case of the famous Bullet cluster, where two galaxy clusters have collided and passed through each other, the gravitational lensing maps show the dark matter continuing on its original path while the hot gas between galaxies has been stripped away and slowed by the collision, providing one of the clearest demonstrations that dark matter behaves differently from ordinary matter, interacting gravitationally but not through the electromagnetic force that causes gas clouds to push against each other and slow down. These lensing techniques have also been applied to the region of the Great Attractor, though the observations are difficult because the area lies behind the zone of avoidance where our own Milky Way's disk blocks our view with dust and stars. But by observing at infrared wavelengths and X-ray wavelengths that can penetrate this obstruction more easily, astronomers have confirmed that the mass in this region is dominated by dark matter, just as in other large cosmic structures, with the visible galaxies and hot gas representing only a fraction of what is gravitationally present. And so we come to the largest pattern of all, the cosmic web, which is the name astronomers give to the overall distribution of matter in the universe, and which reveals itself when we map the positions of millions of galaxies and trace out the structures they form, structures that resemble nothing so much as a vast three-dimensional web or foam, with thin filaments connecting dense nodes and enormous empty voids filling the spaces between. This pattern was first glimpsed in galaxy surveys beginning in the 1970s and 80s, but it was not until computer simulations became powerful enough to model the gravitational evolution of dark matter over billions of years that the full beauty and inevitability of the cosmic web became clear. And among the most influential of these simulations was the Millennium simulation, completed in 2005 at the Max Planck Institute for Astrophysics in Germany, which traced the motion of 10 billion particles representing dark matter through cosmic time, from the smooth early universe shortly after the Big Bang to the complex filamentary structures we observe today. The Millennium simulation and its successors have shown that the cosmic web arises naturally from the growth of small initial density fluctuations under the influence of gravity, with slightly denser regions attracting more and more matter over time while slightly less dense regions become emptier and emptier. And the result is a universe where matter is not distributed uniformly but instead concentrates into sheets and filaments and nodes, with the filaments tracing out paths along which matter flows from voids toward the densest concentrations, like streams of water flowing down mountain slopes toward lakes in the valleys below. The nodes of the cosmic web, where multiple filaments converge, are the sites of the largest galaxy clusters and superclusters, and the Great Attractor region represents precisely such a node, a place where several major filaments come together and where matter has been accumulating for billions of years, drawn by the combined gravity of everything already present, with each arriving galaxy adding its own mass to the total and increasing the gravitational pull on galaxies still farther away. It is helpful to imagine this not as a single point exerting a pull but as a vast region of enhanced density, a place where the cosmic web is especially thick and tangled, with many crossing filaments and substructures and clusters of clusters, all contributing to the overall gravitational influence that we detect through the motion of our local group and our Virgo supercluster toward this direction in the sky. But attraction is not the only force shaping our cosmic motion. And this brings us to a discovery made in 2017 by Yehuda Hoffman of the Hebrew University of Jerusalem and his colleagues, who used sophisticated reconstructions of the local velocity field to identify not just regions that are pulling us toward them but also regions that are pushing us away. Or more precisely, regions where the relative absence of matter means that there is less gravitational pull from that direction, creating an effective repulsion. They called this region the dipole repeller, and it lies in roughly the opposite direction from the Great Attractor, in the southern sky, and it represents a vast cosmic void, a region of space where very few galaxies exist and where the density of matter, both visible and dark, is significantly below the cosmic average, and because there is less matter in that direction, there is less gravity pulling us toward it, which means that the pull from the opposite direction, where more matter exists, is relatively stronger, and so we drift away from the void and toward the concentration, pushed from behind as we are pulled from ahead. This picture of cosmic motion as the result of both pushes and pulls, attractions and repulsions, is a more complete description than simply saying that the Great Attractor is pulling us, because in truth our trajectory through the cosmos is shaped by the entire distribution of matter around us, with overdense regions attracting and underdense regions effectively repelling, and our actual motion is the sum of all these influences, a vector pointing in the direction where the net gravitational pull is strongest, which happens to be roughly toward the Great Attractor but is also influenced by the emptiness of the dipole repeller and by countless other structures both near and far. One might imagine this as a kind of dance, though a very slow one by human standards, with our galaxy and our local group of galaxies responding to the gravitational music played by hundreds of thousands of other galaxies and by the vast invisible reservoirs of dark matter that surround them. And this dance has been going on for billions of years and will continue for billions more, with the choreography slowly changing as structures merge and grow and as the accelerating expansion of the universe gradually alters the balance of forces. The Great Attractor, then, is not merely a curiosity or an anomaly but a window into the nature of dark matter itself, because by studying how matter moves toward this region, and how the mass is distributed within it, and how the gravitational lensing reveals the invisible component, we learn about the properties of the substance that makes up most of the matter in the universe. This mysterious dark matter that we can weigh and map but cannot yet identify, that we know exists through its gravitational effects but whose particle nature remains one of the great unsolved problems of modern physics. The invisible architecture of everything, the scaffolding upon which galaxies form and clusters gather and superclusters assemble, is built primarily of dark matter, with ordinary matter merely following along, falling into the gravitational wells that dark matter creates, lighting up with stars and gas where the density is highest but always tracing a pattern that was established first by the invisible component. And so as we contemplate the Great Attractor and our gentle drift toward it, we are also contemplating the nature of reality itself, the hidden structures that shape everything we see, the cosmic web that connects all things, and the patient work of gravity over billions of years, drawing matter together, building complexity from simplicity, creating the universe we inhabit from the faint initial fluctuations in the primordial darkness. This is a universe of invisible forces and hidden masses, of structures too vast to see all at once and motions too slow to perceive in a human lifetime. And yet it is also a universe that yields its secrets to patient observation and careful thought. As Zwicky discovered in 1933 and as astronomers continue to discover today, each new observation adding another piece to the puzzle, each new simulation refining our understanding, each new telescope opening another window onto the cosmic web and the dark matter that sustains it. And so we return now to this present moment, to this quiet evening or this still and restful night, wherever you may be. lying in the gentle darkness with your eyes perhaps closed or perhaps softly open, breathing in and breathing out, while beneath you the Earth continues its patient rotation as it has done for 4.5 billion years, spinning on its tilted axis at roughly 1,600 kilometers per hour at the equator, though you feel none of this motion, for you are carried along with everything else, the atmosphere and the oceans and the mountains and the sleeping cities, all of it turning together through the darkness of space. And this spinning Earth is itself being carried by the Sun, our modest yellow star, which pulls our planet along on its own vast journey through the galaxy, so that even as you rest here in stillness, you are in truth hurtling through space at approximately 30 kilometers every second, tracing out an elliptical path around a star that is itself not stationary but moving, drifting, falling through the great spiral of the Milky Way. The Sun, you see, is not fixed in place within our galaxy but rather orbits the galactic center, that distant region where supermassive black hole sits quietly in the darkness, surrounded by ancient stars packed closely together, and our Sun traces its path around this center at a speed of approximately 220 kilometers per second, which is to say that in the time it takes your heart to beat once, our entire solar system has traveled some 200 kilometers through the galaxy, and yet you notice nothing of this tremendous velocity, for there is no wind in space to press against you, no friction to slow you down, only the silent and frictionless falling that is orbital motion, the endless gentle tumble of objects caught in one another's gravitational embrace. And so you drift onward, carried by the Sun, which is carried by the galaxy, which is itself being carried by something larger still. For our Milky Way galaxy, home to some 200 billion stars and all the planets and moons and asteroids and comets that orbit them, and all the clouds of gas and dust that drift between the stars, and all the dark matter that surrounds and permeates the visible structure, this entire vast collection of matter is not standing still but streaming through space at approximately 600 kilometers per second, moving in a direction that points toward the constellations of Centaurus and Hydra as seen from Earth. And this motion is not random or purposeless but is the result of gravitational attraction, the gentle persistent tug of the Great Attractor and the structures beyond it. Masses so immense and so distant that their light takes hundreds of millions of years to reach us, yet their gravity spans that void and pulls upon us even now, even as you breathe in and breathe out, even as your body rests in stillness while being carried at tremendous speed through the cosmic deep. And the timescales involved in this journey are so vast, so utterly beyond human experience, that they become a kind of comfort rather than a source of anxiety, for nothing is rushing, nothing is urgent. The Great Attractor has been pulling on our galaxy for billions of years already and will continue to pull for billions of years more, and the distances involved are measured not in kilometers or miles but in megaparsecs, those enormous units that astronomers use when ordinary measurements become too small to be practical. And 1 megaparsec is roughly 3.26 million light-years, and the Great Attractor lies some 250 million light-years away, so that even traveling at 600 kilometers per second, even maintaining this tremendous velocity for age after cosmic age, the journey would require timespans that dwarf the entire history of life on Earth. Timespans during which countless generations of stars would be born and would burn through their nuclear fuel and would die, scattering their enriched material into space to form new stars and new planets. And through all of this long, slow passage, our galaxy would continue falling, gently and persistently, toward that distant concentration of mass. And yet, and here is a gentle truth that emerged from observations made in the late 20th century. We will never arrive. We will never reach the Great Attractor, For the universe itself is conspiring to keep us apart. And this conspiracy takes the form of something called dark energy, a mysterious component of the cosmos that was discovered through painstaking observations of distant supernovae. Those brilliant explosions that mark the deaths of certain types of stars. And in 1998, two separate research teams, the Supernova Cosmology Project led by Saul Perlmutter and the High-Z Supernova Search Team led by Brian Schmidt and Adam Rees, announced findings that shocked the astronomical community and changed our understanding of the universe's fate. For they had discovered that the expansion of space is not slowing down as most scientists had expected, but is instead speeding up, accelerating, driven by some unknown energy that permeates all of space and pushes everything apart. This dark energy, which makes up roughly 68% of the total energy content of the universe, works against gravity on the largest scales. And while gravity pulls galaxies toward one another, dark energy pushes them apart by causing space itself to expand ever faster, and on small scales. Within galaxy clusters and superclusters, gravity is strong enough to overcome this expansion and hold structures together. But on larger scales, across the vast gulfs between superclusters, dark energy wins, and the expansion carries distant regions away from one another at rates that increase with distance, so that the farthest galaxies we can see are already receding from us faster than light itself can travel through the intervening space. Not because they are moving through space at superluminal speeds, but because space itself is stretching, carrying them away on an expanding tide that will never reverse. And what this means for our journey toward the Great Attractor is both humbling and strangely peaceful. For while we fall toward it through local space, the overall expansion of the universe ensures that we will never close the remaining distance. We will approach but never arrive, drawn ever onward by gravity while being gently held back by the stretching of space-time, like a dreamer walking toward a destination that recedes as fast as they advance. And there is no frustration in this. Only the quiet acceptance of cosmic mechanics operating on scales too large for urgency or disappointment. And the Great Attractor will remain forever ahead of us, a gravitational beacon that we follow without ever reaching. And this is simply the way of things in an accelerating universe, where even the strongest bonds of gravity cannot overcome the fundamental expansion of space itself. And in the far future, in eras so distant that human timekeeping becomes meaningless, the effects of this accelerating expansion will become more pronounced, and galaxies that are currently visible in our telescopes will gradually fade from view, not because their stars have dimmed but because the expansion of space will carry them beyond what astronomers call the cosmic horizon, the boundary beyond which light can no longer reach us because space is expanding faster than photons can travel through it. And one by one the distant galaxies will redshift into invisibility, their light stretched to wavelengths too long to detect, until eventually our own Laniakea supercluster will find itself alone in an observable universe grown dark and empty, surrounded by a void that contains no stars, no galaxies, no light from the wider cosmos, only the cold whisper of the cosmic microwave background grown ever fainter as it too is stretched by the expansion. This will not happen soon. This isolation lies trillions of years in the future, timescales so vast that the current age of the universe, some 13.8 billion years, is merely a brief moment by comparison. And during all that time Laniakea will persist, held together by gravity, the Milky Way and Andromeda merging into a single larger galaxy, the local group settling into its final configuration, while the broader structure of our home supercluster maintains its integrity against the expansion, a gravitationally bound island in an ever emptier sea. And any beings alive in that distant era, whatever form they might take, will look out at a sky containing only the stars of their local neighborhood, with no hint of the hundreds of billions of galaxies that currently populate the observable universe, and they may never know what they are missing, unless they find ancient records that speak of a younger cosmos filled with light. But that is the far future, and for now, in this present moment, the universe remains full and rich and interconnected, with galaxies scattered across the observable volume in their hundreds of billions, each one containing its own hundreds of billions of stars, and gravitational threads connect them all, drawing them toward the densest regions, pushing them away from the emptiest voids, weaving a tapestry of motion that spans the entire cosmos, and you are part of this tapestry, lying here in the darkness, carried along by forces that have been operating since the beginning of time, and every atom in your body, every proton and neutron and electron, is participating in this cosmic flow, moving through space at tremendous speeds, falling toward masses you cannot see, fleeing from voids you cannot detect, riding the expansion of space-time itself, which stretches beneath you and around you and within you at every moment. The calcium in your bones was forged in the hearts of ancient stars that exploded billions of years ago, scattering their contents across light years of space, and those atoms drifted and tumbled through the galaxy for eons before gathering into the cloud that collapsed to form our sun and its planets. And now those same atoms rest within you, arranged into living tissue, and they continue their journey through the cosmos, carried by your body, which is carried by the Earth, which is carried by the Sun, which is carried by the Milky Way, which is carried by the gravitational pull of the Great Attractor and the Shapley Supercluster beyond it. And so, in a very real sense, you are not separate from the cosmic flow but are an intimate part of it, a momentary arrangement of ancient matter participating in motions that began long before your birth and will continue long after. And there is something gently wonderful in the contemplation of this truth, not wonderful in any urgent or excited way, but wonderful in the quiet manner of a deep and abiding mystery. For we cannot see the Great Attractor directly. It lies hidden behind the dusty plain of our own galaxy, obscured by the very stars and gas clouds that make our home in the cosmos, and yet we know it is there because we can feel its pull. We can measure the motions it induces. We can trace its influence across hundreds of millions of light years. And this invisible mass, this hidden concentration of matter that we have never glimpsed with optical telescopes, has been shaping the motion of our galaxy and our local neighborhood for billions of years, guiding us along paths we did not choose, drawing us toward a destination we will never reach. And so we drift, you and I and all the atoms of the Earth and the Sun and the stars, we drift through the immeasurable heaven, falling gently toward something we cannot see, pushed by voids we cannot feel, carried by the expansion of space itself, which flows beneath us like an infinite and silent river, and there is no destination that we will ever reach, no final resting place where the motion stops, only the endless gentle passage through the cosmos, the perpetual falling that is the fate of all matter in an expanding universe. And this falling is not a tragedy but simply the way of things, the natural state of existence in a cosmos governed by gravity and expansion, where nothing is truly still and everything is in motion, and the motion itself is a kind of peace, a cradling by forces far larger than ourselves, and we are held by these forces as surely as we are held by the earth beneath us, supported and carried and guided through the darkness. And now, as you rest here in this quiet moment, you can let yourself feel, if only in imagination, the tremendous journey you are taking, hurtling through space at speeds beyond comprehension while feeling only stillness, falling toward an invisible mass while feeling only rest, and the universe carries you onward through its deepest currents, those great flows of matter and energy that have been streaming since the beginning, and you are part of them, woven into the fabric of cosmic motion. And there is nothing you need to do, nothing you need to understand completely, only this gentle awareness that you are being carried, that you are falling, that you are drifting peacefully through the night, cradled by gravity and expansion and the quiet mechanics of an ancient and ongoing cosmos, moving ever onward through the immeasurable heaven toward a destination that recedes as you approach, forever falling, forever at rest, forever home.